take control of your equipment data, and unlock the benefits of design optimization.
Thanks, Max. Thank you very much. Thanks to the guys. That presentation was very informative. I've never really realized how much goes into these projects before a shovel gets in the ground. It's generally where I've been engaged. So yeah, I'm going to talk about something today that is a little bit more further along in the project process. I'm going to talk about design automation in the context of advanced facilities and pretty much focus around the MEP side of the equation where the rubber really hits the road when you're trying to get these factories up. My background is in projects, and I did a little bit of pharma when I started out, but mostly for the past 10 plus years I've been working in semiconductor, both on the client side and on the EPC side. But about 6 months ago, I decided to join Basesite, and I just decided to join Basesite because I could see that these guys were doing something new and innovative in the design space. And from my project experience, I knew that projects need these new solutions because they're getting more and more challenging. Because of a number of factors, because of external factors like the market conditions, the labor shortages that we see, the cost escalations, but also because of internal factors, because they're getting much more complicated every year. So I'm going to talk about that complexity a little bit and why things are getting harder to do. So a bit of a timeline here, and I'm going to really focus this around semiconductor, and I hope most people have some exposure to semiconductor and understand the terms that I'm going to use, but if you don't, please stop me and I'll explain. So number one, the tools have got more complicated. Okay, so the chip in your phone got smaller and it got harder to make that chip. So we need more and more complicated tools. On the far left, you can see a lithography machine from the early 90s. Looks like maybe a vacuum pump skid or something what you would regard as quite a simple piece of machinery these days, but at the time it was cutting edge. Moving through to the mid-2000s, immersion lithography scanners. At the time, we thought this is the most complicated thing we've ever seen. This is such a challenge to make these tools work. But then we get to where we are now, 2020. You can see a extreme ultraviolet lithography machine. It's about the size of a bus. It comes on 5 747s, costs about $150 million. And one tool uses about 2 MVA of power. And in a leading edge factory, you maybe put 30 of these tools in. So complexity has grown at the micro level. At the macro level, typical 8-inch fab from the early 90s, 50 to 100,000 square feet. Now we're at more like 500,000 square feet for a mega factory. Reasons for this, the tools have gotten bigger. We've gone from 8-inch to 12-inch wafers, and generally the manufacturers want to take advantage of scale. Okay, so the facilities have got bigger, and what goes into the facilities has got more complicated as well. So a typical fab, you're going to have a number of electrical systems and multiple voltages across those systems to cater for the various use cases in the tools. And on the process mechanical side, to deal with the growth and complexity of the process and the scale of the process, the amount of systems required has grown dramatically. So on the exhaust side, whereas back in the early 90s you might have had a scrubbed exhaust and a general fab exhaust, now you have 6 different exhaust streams because you got to segregate everything to get all the nasties out of it and provide different pressures to the tools, etc. You're going to have 3 or 4 vacuum systems. You're going to have maybe 5 different compressed air systems, different pressures, different purities. You're going to have 10 bulk gas systems, maybe more. As the demand grows in the facilities, these systems that used to be on bottles now come on isotainers or tank farms or even from an air separation unit. Multiple ultra-pure water systems, ultra-pure water, softened water, roadie water, hot ultra-pure water, lithography ultra-pure water, reclaim ultra-pure water. Again, the process is just getting more and more complicated. And aqueous waste, kind of the same as on the exhaust side. The need for the clients to separate out the different nasties that come out of the process has grown as the complexity increases. Gas and chemicals, last fab I worked on had about 30 aqueous systems, 50 specialty gas systems, and 50 planar chemistries. So you start to get the picture. It's a very, very complicated thing that we're putting together. So how do we manage these complex inputs? Okay, so you know, we've got this facility, we've got this complex manufacturing picture, and we need to translate that into the scope that we need to execute, to design and execute to deliver the project. So the first job is to translate one into the other, okay? And we can kind of say broad strokes. We know we need a BCP, it's got to be X hundreds of thousands of tons. We need a UPW building that's going to be X GPM. We can sort of define those larger parts of the projects very early with kind of pro rata information or based on benchmark information. But at some point in time, we need to hook the tools into the facilities. And that's an activity that's on the critical path, and that's the activity that I'm going to focus on now. So there's a little cutaway, oh, wrong one. Little cutaway section of a fab here, very simple, okay? All your process tools in here. You got all your sub-fab utilities in here, so all these pipes running horizontally, and provide all the process mechanical and gas utilities to the tools. Underneath, we've got the electrical distribution system, and we've got chemical and gas distribution cabinets in there as well. So this is what we call the layout dependent scope, or the sub-fab fit out. And the approach that we take, that Basesite take to design, is how do we execute this element faster, do it cheaper, and do it in a more predictable manner, because the process of ramping the factory, installing the tools, is where things get really complicated, and that's where delay occurs, and rework occurs, and new scope that's unforeseen occurs. Okay, so yeah, what does this involve? We generally start with project inputs, okay? So this is back one. This is a typical layout, right? It's just a 2D drawing that says these are all the tools that go into the factory. And then we also get, generally, a tool utility matrix, which is like an Excel document. It summarizes what all the tools use in terms of utilities, electrical, P2LS, gases, etc. Okay, so we get that as an input from manufacturing. Sometimes we get it like that. Sometimes we just get a dump of files from different tool vendors, and the guys say, hey, good luck, off you go. So we got to take all this and we got to translate it into this scope before or below, the laterals and the electrical and the gas and chemical systems. And this element of scope in terms of the production building is about 30% of the cost. So how does the complexity, the growing complexity of these facilities impact how our ability to deliver this? Okay, so 3 key areas, right? It impacts our ability to deliver a design that gives cost efficiency. So semiconductor is all about speed, and it takes time to translate that complexity where you've got a couple of thousand tools in a factory, you've got a couple of 100,000 connections to those tools. It takes time to turn that into scope, and engineers don't have time to hang around. So they kind of design by area, they add gross margin, they add fat to the design basically, and that's how to get the job done quickly or in the appropriate amount of time. But what we see come out of that is very low utilization on the facilities, so it costs the client more. For the same reason, the ability to produce timely critical design output is impacted. So you've got all these numbers to crunch, it's data to get through to say what needs to go into the facility. That takes time. And this layout-dependent activity is critical path. You know, so typically crunching these numbers for a big fab can take 12 weeks, and that's just not an acceptable duration of time, or it creates significant pressure on the project. The ability to integrate the delivery of base build and tool install. So typically, in my experience anyway, tool install is executed as maybe a CMS type contract arrangement direct to the client or multi-prime, and the tools kind of get designed one by one after the base build design has been complete. And what happens is the two designs become divergent, and the rules that the base build designers assume tool install would stick to, they don't stick to, and it creates all sorts of problems that I'll talk to in a minute. So we want to put a process in place to make this easier, okay? But it's difficult because there's such diverse inputs, right? We've got multiple different parties inputting to the project scope. We have operations, we have manufacturing, we have compliance to specifications for statutory reasons or whatever. And understanding this documentation is very, very challenging, and I've been involved in numerous efforts just trying to pick through documentation or pages and pages of Excel or schedules, people locked in rooms for weeks just trying to figure out what the hell is going on with things. But now we have more sophisticated tools to approach these kind of problems, to feed into the process that we want to put in place to make this easier. So we can use things like PDF scraping, Excel harvesting, document harvesting to get the information that we need out and put it in a format that allows us to do powerful things. And then where more sophisticated tools are needed to get this information out, everybody, you know, you want to be living under a rock to not be aware of AI, but, you know, most people think of it in terms of large language models and your ChatGPTs, but there's other tools under that umbrella that we use to extract information. So one of the things we use is optical character recognition, which is computer vision, basically allowing computers to see things in drawings. And how we use that is, I talked earlier about the tool layout drawn. One of the things we want to know is where is each tool in an XY coordinate. Well, layout drawings don't tell you where the different points of connections to the tools are in the Z coordinate. And if you have a look, if your eyes allow it, you can see on this drawing, this is a tool install design schematic, or which you get from a tool install AE or maybe from the vendor. You can see these little triangles, okay? And that nomenclature dictates a point of connection between, an interface point between the tool and the facility. So we use OCR to look at these drawings and say, okay, what OCR does is identifies where there might be text, identifies what in that area is a line of text, what in that line of text is a character of text, and then it converts that to a bitmap image, which is basically a digital representation of the image. And then once it's in that format, we can put it through a machine learning pattern recognition algorithm that will basically extract from this drawing where those triangles exist and where they are on the various fab, sub-fab, utility level areas. So now we've got our Z coordinate, and we can apply that to the total database that we have of all the tools. And then we've got the pieces of the puzzle that we need to continue with our process, right? So this is our process. This is how we plan to sort of address and automate this activity of turning the manufacturing requirements into the scope for the project, for the layout-dependent element of the project. So we take in the factory layout data. We talked about that already. That's the layout. That's where all the tools are in X, Y. We glean our Z coordinate from our OCR. We take our tool utility data from whatever source we have. So now we know for each tool in its location what facilities it's required to run it. And we take our system engineering specification. So that's going to say, you can't put these tools on this panel together for whatever redundancy reason, or your max allowable velocity in your lateral is X feet per minute for vibrations reasons. It's going to dictate all the owner's requirements and the schedule and the ramp requirements, okay? So, one of the things that never really happens as part of tool install is things are not assigned to base build facilities in a logical way. So you end up looking at your early ramp tool set and finding out that the plan is to put it on a panel over here, and a panel over here, and an OFA service over here, and an OFA service over here, and you end up concentrating on more work than you need to bring the factory up. So we want to put all this stuff into the hopper, and I'll explain in a little bit more detail in a minute or two how that hopper works. But basically what we want to get out of that is we want to get our long lead equipment list, we want to get some kind of definition of our long lead material, and we want this interface of the tool install and the base build connected, okay? The two things locked together, and we call that 100% assignment. Okay, let's move on one. Okay, so how do we do this? And this gets a bit complicated. I'm a facilities engineer, I'm not a data scientist, so I'm going to try and talk to this in a way that I can and that hopefully all of you can understand as well. But please stop me again if I'm being too complicated. So basically what we do is we take all the tools and we say in XYZ, this is where the tools exist, right, in our data model. And we associate all that utility information with the tools, and we say, okay, this is where I need this utility, this is where I need this utility. And then we create a hypothetical scenario for the facilities that supply those tools, okay? So if you think about underneath the fab, underneath the factory floor, we use an electrical example, a 1 foot by 1 foot grid, and you say, on every intersection of that grid point, you can put an electrical panel. So we might create 10,000 hypothetical electrical panels. And then we'll run an algorithm that will see how can I connect these tools to these proposed panels and remain compliant with the engineering spec that you've defined. So we're going to create all these possible options, and what we'll end up with is, here's 10 million different ways that the tools could collect into the facilities. So obviously people can't really work that way, right? But machines can, and that's kind of the beauty. So now that's going to leave us with a selection, basically, for all our facilities for the fab of how all the tools in the fab could potentially connect into potential locations for panels. And then what we're going to do is we're going to feed that into an optimizer, right? An optimizer is an algorithm that uses linear programming and regression to refine complex sets of data into something simpler based on input criteria that specifies what you want to get out of the end result, right? So, for example, I'll say electrically again as well. We would say to the optimizer up front, you know, maybe we've got a good rate on panels. Panels are cheap. We want you can use as many panels as you want, but we want you to minimize the length of the tool install cables between the tools and the cables. Or we've got a really bad rate on panels. We want you to minimize the number of panels in the facility. So you can kind of tweak it that way. So it's going to go through all those options, and it's going to say, okay, here you go. Here is the optimum set of connections between the tools, and here is the list of facilities that you need to install to hook up to those tools. So the output of this is basically, this is the plan to connect the manufacturing to the facility, and here is a list of the chemical cabinets, the gas cabinets, the laterals, including their sizes, their number of points of connections, and the electrical cabinets for all the different voltages. Have I lost you? Definitely nearly lost myself. Okay, so I'll kind of wind it back a little bit. So, you know, the benefits of this approach. So we see increased speed of design output, and I'll talk to it in a little bit more detail in a minute. This is all about automation, right? This is all about taking tasks that people used to do using traditional methods before and allowing a computer to do a representation of that. So it's always going to be quicker. And it's really repeatable. Like, if you come to me and say, okay, for my 250,000 square foot fab, I want you to produce all of these deliverables that I described, the equipment lists and the assignment matrix, I can do that in less than a week. And if you give me a new factory layout, I can do it again in a week straight away. Or you want to totally change some criteria in your electrical distribution system, we can rerun that in a day. And that power never really existed before. So it's faster, okay, and it reduces cost. And I will speak to that in a bit more detail as well. But the optimization, as I kind of alluded to, increases the facility utilization. So we maximize how many tools connect into the facilities. We lower the number of facilities. Before, with the approach, with the limitations of human design, people just needed to add more in to know that they were covered themselves for the future. So it reduces cost. And as a function of that CapEx cost reduction, we get a reduction in engineering cost, but also this process of simply doing what we would call a gap analysis traditionally is much more reduced. And we get predictability in execution. And I'll show you a really good example of that in a minute, but it's all about having all those tools assigned to those facilities. It's so challenging. Every project that I've done, we get to, 6 weeks before the ETS, RTS tools are supposed to come online, and people are running around like crazy trying to figure out what connects to what, or you figure out your tool's supposed to be in 2 weeks and the point of connection assigned to is sterilized, or you can't use that point of connection because some other tool is connected to it that you're not supposed to co-locate with. It's all about predictability, getting rid of those unforeseen delays. Okay, so yeah, this is just a bit of a closer look at the speed increase, right? So what I'm representing here is the process of getting that release of information from manufacturing, right, in the red. And traditionally what we did, and this is my experience, and it's different for every project, right, but for a large fab, we go into what's called a 12-week gap analysis process. And what we do in that is we define all the scope that needs to go into the factory that we didn't know about before. So in the initial stages of a greenfield, that's everything, basically. So 12 to 14 weeks for that overall process, but the elements of the scope we're really focused on now, typically an output after 6 weeks, where you get a long lead list with, here's all your laterals, here's all the Petrobras cabinets, chem and gas cabinets, here's all the electrical distribution system. So we can do that in a week, okay? So that's a 6-week win back on a project that is constantly under schedule pressure. There are other ways you can achieve schedule wins in this regard. You can do partial buys, you can go at risk, but what we're saying is, why should you need to go to a supplier and buy 30% up front and the remaining 70% later, lose commercial leverage over them, when you can do it all in one go, have the information a week after it's released. Okay, cost, right? So this is a big one, okay? So this is some data from a fab that we did in Europe, and it's a pretty big fab, as you can tell from the numbers. The baseline design had 792 electrical panels in it. When we came in and optimized it, we said, hey guys, you can connect this tool set and you can do it with 534 panels, okay? As an important point to emphasize here is this is not like a balloon squeeze. It's not like you take panels out and you just add more tool install cabling in. This is a reduction across the board. You can see a 20-kilometer reduction in cable length. So the main reason for this, as I said, is this low utilization of facilities. So I don't know if you can read that, but these are bins, right? 5%, 10%, 15, all the way up to 100. And the bar is showing the utilization, basically. So in this design, nearly 100 of those panels were only utilized to 5 to 10% of their circuit or load capacity, which is phenomenal if you show that to an owner. So again, I really should have included the new utilization figures. I didn't for some reason, but you know, you can see it here. This is the output, right? We increased that facility's utilization and we reduced cost. So this is just a little example of how these execution problems, and these are quite understated, but if you've done a couple of these projects, you'll have known these pains before. You know, what basically happens is, you know, we've got these 8 tools, right? And the plan was we were going to provide these 2 panels, and they were going to facilitate those 8 tools. But what happens is these tools got designed first, okay? And they all came along and said, well, we like this panel the best because it's the easiest one to get to. And when it came to install this tool, there was no capacity left on this panel, or chem cabinet, gas cabinet, whatever it is. So the guys were left with a decision. Do we route to the one that's further away, that's non-spec compliant? Say it's a chemical line and you exceed your maximum allowable limit for it. Or do we spend 200K and install a new panel? And generally you only find these problems at the back end of the project, so there's no money. So the answer is make a compromise. But what happens then is 6 months down the line, manufacturing ring up and say, we've got a yield excursion on this tool, what's going on? And you find out the problem is because you installed this long line, you're now getting chemical deposition in it and you've got particle shedding going into the tool. Or another example, if this was electrical, this tool got loaded onto this panel. It turned out these were like tools from the same fleet, and to do a PM or some kind of downtime on the panel, you had to take down the whole fleet and get an impact to production. So these are nasty surprises that you get later on, and this all comes back down to base build does its job, looks at what it thinks the scope is, and then tool install comes along on a one-by-one basis and says, I'm just going to do what's convenient for me for this tool right now, and doesn't adhere to the overall specifications. Okay, that's about me. Anybody got any questions? Hey.
Councilor with Yates, what's the lead time on building the logarithm for each project, or is it a standard?
So it doesn't need to be built for each project. Like it's generic. That's kind of half the way we do business. We have to be able to handle these diverse inputs that come in. It depends, obviously, on what the size of the fab is and what the quality of the data is like. You know, if the data is bad, there might be a significant cleanup period. It could be a couple of weeks. I can't really give you a straight answer without knowing how big the fab is. You know, but it's not significant. Okay, our whole philosophy is that we need to be adaptable to these inputs.
There's a question here in the far back.
Hey.
How do you go about implementing this into a design project?
Yeah. So it depends on how the project is executed, right? So like, you know, some clients are very mature in their approach to construction. They're very sophisticated, and that's kind of the side of things I've come from. And if that's the case, you know, this can be with, the client can use this basically and say, okay, I'll define this, and now I've got my list of equipment material. I'm going to give this to you, the contractor, and say, this is the scope, go. You know, so that's one execution model. Or you're in a design build execution for a less sophisticated client who just wants to pay you and get the keys when you come back with the fab, and then it's on the AE side.
Okay, there's another one here.
How do you work, Mike Mullen with Aptitude,
Hey.
how do you work standardization into your design? How do you, what rules, what procedures do you have in that aspect?
Standardization, standards themselves, like,
Well, no, as far as prefab is becoming a very large part of computer chip factories. How do you say, okay, this set of tools down this column
I get you.
in the area,
Yeah,
we're all going to put in 6-inch acid waste
I'm with you.
chemicals all the way down. Do you work at that?
Yeah, I'm with you. So, two ways, okay? Maybe the client already has their proposed, let's talk about a lateral rack, you know, and they say, look, this is our standard lateral rack. So we would use that as the kind of selection box of what types of laterals we will put in. We work within that framework. We limit the program to say, you can only select a 40-inch Teflon-coated stainless with 50 POCs for a scrub exhaust, or you can only select a 4-inch high-purity nitrogen. So that's one way to do it. Or the other way is we can define that by looking at the input data and saying what the optimum sizes for those facilities will be.
I got a question for you, Andrew, and you know, I talked a little bit about yesterday. So is there any concerns from the way of how you guys do the work through the software, right, or through the development, based on the size of the tool, right, whether we're talking about a 2-point of connections, right, or we're talking about with the litho, right, it could be a 200-point of connection. Is there any challenges with that?
There is. One of the challenges is understanding where they are in fab level, sub-fab level, utility level that we talked about before. You know, other than that, it's kind of like a data quality issue. So like if the tool is represented incorrectly in the UM, so I think we talked about manifolding yesterday, say that's not disclosed, we will just see what is proposed basically, you know, in the utility matrix. So with any of these things, you know, there is a bad data in, bad data out type problem, but we try to be as flexible as possible to deal with stuff like that.
And how receptive have been the AEs, right, or the owners on this type of development that you guys have in place?
Well, the owner's very receptive.
Not much of the AE?
AE is receptive if they're the one using it, but maybe not so much if the owner is using it. So look, I guess at the end of the day, what this does is reduce the engineering effort that's required. You do an amount of upfront work, and then it's there, functional for you, the same as any other automation procedure or adding any machine to a process. And then you don't need to do that work again. But, you know, the AE could say, well, this is great if I'm going into bid for projects and my competitor doesn't have it because I know I have a cost advantage. Or, you know, could say, not so good if the client already has the work done and then comes saying, hey, because we're not doing the full design, right? We're defining what that network of the distribution system, the architecture of it looks like. Somebody's still got to go off and model it. Somebody's got to still produce the 2D drawings. They've got to stamp the drawings, all that kind of stuff. So, you know, we're just looking to speed up an element of the process that has too much manual effort at the moment, and there's no reason for it to take that long.
Okay, great. Any other questions? Got one in the back.
Hey.
How do you handle change? So, say the tool sets change often.
Yeah.
So if the tool sets change often,
Yeah.
how do you know when to re-optimize and run that compared to like constantly having to run it?
Yeah. Well, I guess like it's probably one of the most constant things, no matter where you work in semiconductor, is everything's changing all the time. And you know the reason for that is short market times. You've got technology that's leading edge, and these guys just want to tweak it and get it right and make as much money out of it as possible. So yeah, certainly in my background with who I've worked in, it's been a constant. Typically though, it's been controlled in some mechanism, you know, whether the change gets communicated quarterly or every half a year. That's an agreement between the programs delivering it and the manufacturing teams transmitting that change. Like, we can run this every week once it's set up, you know, and that's the beauty. Like, one of the things, when I was at Intel, like, I'd have these constant conversations with the factory, and they'd say, look, we want to put 10 tools here, but we want to know, can we put these 10 tools here or here? What's it going to cost? I said, well, look, I can give you that answer, but I need to sequentially basically do the same job, and it's going to take 6 weeks the first time, 6 weeks the next time, and 6 weeks the next time to say, do you know what, forget about it, we'll just put it here. But what this gives you is the ability to make those kind of decisions, to have that kind of information. You know, because maybe you don't run it for all systems. You just want to know, what does it mean for the big hitters? What does it mean for the chems and the gas and the electrical and the large bore pipe? And you can really quickly tweak stuff and give that feedback. So, like, it gives a level of flexibility that actually makes the question that you're asking much more easy to deal with than it was before, because you don't have that duration.
One last question here.
In what timeline that you have here, do you bring in the installer?
Yeah.
Where in this do you sit down with them and say, this is what we want to do, this is our design?
Yeah.
How will this work?
Yeah. So the point about that would be, so the tool install program is going to start up, okay, at some point in time after this. And, you know, they're going to start one by one installing their tools. And yeah, you're going to get to a position where they don't like the point of connection, or they think that doesn't work. And that's fine, right, as part of the iterative design process of tool install. But the point is, it's from a position of control, okay? Because you understand what the plan is for all tools to connect to all facilities, and you've got a system in place to manage when somebody requests, can I change something because it doesn't work for me? It keeps you in a state of control. So those guys can come along and say, yeah, that doesn't work, I don't like the looks of it. But they're not gonna not use one point of connection, go take something else that's convenient and screw up the plan for the next tool down the line. That's kind of the philosophy. Okay?
Okay. Thank you, Andrew, again. Andrew Johns from Basesite.
Thank you very much. Thanks, Chris.
Okay, we're running 2 minutes early, so